Welcome to our deep dive into the fascinating world of electricity. In this chapter, we'll explore the fundamental concepts that power our modern lives, from the basics of electric current to the intricacies of circuits and safety. Whether you're curious about how your devices work or want to understand the science behind everyday technology, this journey will illuminate the key principles of electricity. Let's begin by understanding what electric current is and how it is measured, setting the stage for everything that follows. Electric current is the flow of electric charge, usually carried by electrons through a conductor like a wire. It's similar to water flowing through a pipe, but instead of water, it's tiny charged particles moving. The amount of current is measured in amperes, or amps for short, using a device called an ammeter. The higher the current, the more charge is moving through the circuit per second. Understanding electric current is essential, as it forms the backbone of all electrical devices and systems. Electric potential refers to the ability of a point in a circuit to do work due to its electric charge. Think of it as the pressure that pushes charges through a circuit. The potential difference, or voltage, is the difference in electric potential between 2 points. It's what drives the current from one point to another. Voltage is measured in volts using a voltmeter. Without a potential difference, there would be no flow of current in a circuit. Ohm's law is a fundamental principle in electricity. It states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points, provided the temperature remains constant. The formula is simple: V equals IR, where V is voltage, I is current, and R is resistance. For example, if you have a 10-volt battery and a resistor of 2 ohms, the current will be 5 amps. This law helps us design and analyze electrical circuits efficiently. Materials can be classified as conductors or insulators based on how easily they allow electric current to pass through. Conductors, like copper and aluminum, let electricity flow freely due to their loosely bound electrons. Insulators, such as rubber and glass, resist the flow of current, making them ideal for protecting us from electric shocks. Understanding the difference helps us choose the right materials for wiring and safety in electrical systems. Resistance is a property of a material that opposes the flow of electric current. It determines how much current will flow for a given voltage. The unit of resistance is the ohm, symbolized by the Greek letter omega omega. High resistance means less current flows, while low resistance allows more current. Resistors are components specifically designed to provide resistance in circuits, helping control the amount of current. Resistance of a wire depends on its length and thickness. A longer wire has more resistance because electrons have to travel a greater distance, facing more obstacles. Conversely, a thicker wire has less resistance, as it provides more space for electrons to move. This is why power lines are made thick and as short as possible to minimize energy loss. Understanding these factors helps in designing efficient electrical circuits. Series circuit is one where components are connected end-to-end, forming a single path for current to flow. If any part of the circuit is broken, the entire circuit stops working. Series circuits are simple to design but have limitations, such as all components sharing the same current. This setup is commonly found in string lights, where one broken bulb can turn off the whole string. In a parallel circuit, components are connected across common points, creating multiple paths for current to flow. If one path is interrupted, the others continue to work. This makes parallel circuits ideal for home wiring, where turning off one light doesn't affect others. Each component gets the same voltage, but the total current is divided among the paths, making this arrangement both practical and reliable. Pairing series and parallel circuits helps us understand their strengths and weaknesses. In series circuits, all components share the same current, and a break affects the whole circuit. In parallel circuits, each component operates independently, and the voltage remains the same across all branches. This is why most household wiring uses parallel circuits, ensuring reliability and convenience in daily life. An electric current flows through a conductor, it produces heat. This is known as the heating effect of electric current. For example, electric heaters and toasters use this principle to generate warmth. The amount of heat produced depends on the current, resistance, and time. This effect is useful in many appliances, but can also be a safety concern if wires overheat. An electric fuse is a safety device designed to protect circuits from excessive current. It contains a thin wire that melts and breaks the circuit if the current exceeds a safe level. This prevents damage to appliances and reduces the risk of fire. Fuses are commonly found in household wiring and electrical devices, acting as the first line of defense against electrical hazards. Electric power is the rate at which electrical energy is consumed or produced in a circuit. It's measured in watts W. The formula for power is P equals VI, where P is power, V is voltage, and I is current. Understanding power helps us determine how much energy an appliance uses and how much it will cost to operate. This concept is crucial for managing energy consumption efficiently. Electrical energy is the total amount of work done by an electric current over time. It's calculated using the formula, energy E equals power P times time T. The unit of energy is the joule J, but in households we often use kilowatt-hours kWh. This calculation helps us understand our electricity bills and manage our energy usage more effectively. Safety is paramount when dealing with electricity. Always use insulated tools, avoid handling appliances with wet hands, and ensure wiring is properly installed. Never overload sockets and use fuses or circuit breakers for protection. Regularly check cords and plugs for damage. These precautions help prevent accidents, injuries, and damage to property, making your environment safer for everyone. Simple electric circuit consists of a power source, wires, a switch, and a load like a bulb. When the switch is closed, current flows from the power source through the wires and the load, lighting the bulb. If the switch is open, the circuit is incomplete and no current flows. This basic setup is the foundation for understanding more complex electrical systems. Switch is a device that opens or closes an electric circuit, controlling the flow of current. When the switch is on, it completes the circuit, allowing current to flow. When off, it breaks the circuit, stopping the flow. Switches are essential for safely operating electrical devices, giving us control over when and how electricity is used. Resistor is a component used to limit or regulate the flow of electric current in a circuit. By providing resistance, it helps protect sensitive components from excessive current. Resistors are found in almost every electronic device, ensuring that circuits operate safely and efficiently. They come in various sizes and values, tailored to specific needs. Voltmeter and an ammeter are both measuring instruments, but they serve different purposes. A voltmeter measures the potential difference, voltage, between 2 points in a circuit and is connected in parallel. An ammeter measures the current flowing through a circuit and is connected in series. Using the right instrument ensures accurate readings and safe experimentation. Resistors use color bands to indicate their resistance value. Each color represents a number, and the sequence of colors tells you the resistance and tolerance. This system allows for quick identification and helps ensure the correct resistor is used in a circuit. Learning to read these codes is a valuable skill for anyone working with electronics. Superconductivity is a phenomenon where certain materials conduct electricity with zero resistance when cooled below a specific temperature. This means electric current can flow indefinitely without energy loss. Superconductors have exciting applications, from powerful magnets in MRI machines to future energy-efficient power grids. However, achieving and maintaining the required low temperatures remains a challenge. Electricity is everywhere in our daily lives, powering lights, appliances, computers, and more. From charging your phone to cooking dinner, we rely on electric current for countless tasks. Understanding the basics of electricity helps us use it more safely and efficiently, making our lives easier and more comfortable. Renewable energy sources like solar, wind, and hydroelectric power generate electricity without depleting natural resources. These clean sources are becoming more popular as we seek to reduce our environmental impact. Understanding how electricity is generated from renewables helps us appreciate the importance of sustainable energy for the future. Electricity and magnetism are closely related. Moving electric charges create magnetic fields, and changing magnetic fields can generate electric currents. This relationship is the basis for electric motors, generators, and transformers, which are essential in modern technology. Understanding this connection opens the door to many exciting applications. Every electronic device contains electric circuits that control how electricity flows. From simple flashlights to complex computers, circuits determine how devices operate. Learning about circuits helps us troubleshoot problems and understand the inner workings of our favorite gadgets. Grounding is a safety measure that directs excess electricity safely into the earth. It protects people and equipment from electric shocks and damage caused by lightning or faults. Proper grounding is essential in all electrical installations, ensuring a safe environment for everyone. Circuit breakers are automatic switches that protect electrical circuits from damage caused by overload or short circuits. When too much current flows, the breaker trips and disconnects the circuit. Unlike fuses, circuit breakers can be reset and used again, making them a convenient and essential safety feature in homes and buildings. Static electricity is the buildup of electric charge on the surface of objects, often caused by friction. It can cause small shocks when you touch a doorknob or make your hair stand up after removing a hat. While usually harmless, static electricity can sometimes damage sensitive electronic components, so precautions are taken in certain environments. Lightning is a dramatic example of electricity in nature. It occurs when static charges build up in clouds and discharge to the ground, creating a powerful flash of light and sound. Lightning demonstrates the immense power of electric forces and reminds us of the importance of respecting electricity in all its forms. We've covered the essentials of electricity, from understanding current, voltage, and resistance to exploring circuits, safety, and real-world applications. These concepts form the foundation for further study and practical use of electricity in daily life. Remember, respecting safety guidelines and understanding how electricity works can help you make smarter, safer choices every day.